so let's begin. Thank you very much to all of you for coming here, and it's my great pleasure, and I consider it a great honor for me to introduce Professor Bhaskar. So before I give just the final formal introduction, let me tell you just one thing. And I was amazed to see that somehow my impression was also mimicked by someone else. I'm not naming who. This morning so we were very scared of you. Extremely scared. So this morning I asked someone else, would you like to meet him? The first comment that he could come up with is, I'm really scared. So, so he is one of the world's leading theorists on social strategic formation of social networks. And he has an astounding array of publications starting from restart to change to example behavior and economic. So just a few months back I could visit Ashoka University where he is currently teaching. It's part-time with Warwick University in Ashoka University. So then I could extend an invitation and visit and he accepted. Then Pritha went forward with the whole arrangement, so I'm grateful to you for the all of those things. So today we'll talk about formation of partnerships in social networks, which is pretty typical of this kind of literature. So I'm sure we'll have a great time. We can have about 1 hour and 15 minutes and we can take questions as you like. So thank you very much for coming.
So thank you for inviting me here, and I guess 1 hour and 15 minutes is too short a time to convince you that I'm not as scary as Anindo has made me out to be. So as you'll see, so this paper has both a theory component and an experimental component, and there was almost perfect division of responsibilities as far as the work was concerned. So Francis and I did the theory, Stefan and Minzu did the experimental part, and for obvious reasons most of the talk is going to be about the theory part. But I've sent you a copy of I've sent Pritha a copy of the paper, so if Jivant has convinced you to be an experimental economist, you can take a look at the second half of the paper. So what's the motivation for this? Well, there is ample empirical evidence that social networks play a big role, an important role in many contexts, exchanging favors, importantly getting information. So the first person to actually point out the importance of social networks as far as employment is concerned is actually a sociologist, Mark Granovetter, who pointed out that informal networks, social contacts, play a huge role in transmitting information about jobs, etc., and so on. What we want to focus on in this paper is not sort of global networks, but the formation of pairs or dyads, as they're called in the sociological literature. And again, one reason for that is you can think of many contexts in which indeed individuals form pairs. For instance, an obvious example is marriage, couples, informal insurance in developing economies, formation of pairs to exchange all kinds of different kinds of favors, mowing almost trivial ones like mowing the lawn, to more complicated ones. This paper we propose a model where agents will explore these networks and to form these bilateral partnerships. When I say we propose a model, I should point out that there's an earlier paper which is very similar to ours. I'll mention that in a minute. And what we want to look at is what are the forces which sustain the network, this formation of pairs, stable dyads, in particular when sustaining these networks involves a cost. There is a large literature actually, well, there is a substantial literature where formation of coalitions, networks, relationships is based on the notion of social punishment. So there are social norms, maybe in an informal society, in a village, let's say, if one household has an idiosyncratic shock, then that household's neighboring household is supposed to provide assistance. If the household doesn't do that, then there's some kind of social ostracism. And of course, that will lead to the formation of stable exchange of favors, as we'll call it here. And that's actually been modeled, not just in one paper, but fairly extensively. What we focus on here is just the simple idea of reciprocity. There's no, as you'll see very soon, there's no punishment, there's no social punishment. And if an individual decides to form or decides to give a favor to another individual, simply out of the fear that if he or she doesn't do it, then the other person is going to punish him. And the consequences of that is what we'll call reciprocity, the idea that reciprocity can sustain relationships. And so this is what we focus on, and the question we want to ask is, what kind of social structure, what kind of network will support the efficient formation of networks? In our model, efficiency has a very simple connotation. It simply means can the largest number of pairs form? Okay? And I'll give you an example very shortly to explain what that means. What are the main results? And again, when I say results, obviously I'm referring to the theoretical results. So first, if the cost of providing favors is positive, then surprisingly any network is going to support the efficient formation of partnerships. In other words, the largest number of pairs possible given the network will form, okay? and be sustainable. That's the important thing. On the other hand, if the cost of providing favors is negative, so you actually get a benefit, for instance, hopefully in marriages, someone proposes to you, and if you accept, that's like giving a favor, or we call that giving a favor, but that presumably that gives you a positive benefit. So then the cost is negative. And then, well, you require more stringent conditions on the network to form the largest number. Let's ignore what we mean by completely elementary networks. We'll come to that later. But the basic idea is that somewhat paradoxically, if the cost is positive, then any network sustains efficiency. If the cost is negative, that is, you actually get a benefit, then then you require a more stringent condition on the social network. Okay. Let's forget. So here's some related literature. Again, there's at least a couple of papers that we are aware of modeling informal insurance and social networks. Francis himself has a paper with Garance Jenico and Debraj Ray that is looking at social punishments. There's a norm of giving help. If a household suffers an idiosyncratic shock, if you don't, then there's social ostracism, and that's a driving force in their model. Then there's some papers on social collateral and exchange of favors, which is not that closely related to our work. This is the paper I mentioned, Jackson et al. Again, their model of favors is very similar, formation of networks is very similar to ours, but they focus not on reciprocity but social punishment. A very different strand of the literature is this papers on bargaining in networks, Mihai Manea, Dilip Abru, Mihai Manea. The reason why we mentioned this is that we became aware of these papers. We are not very well read because these papers were published long before we started working on it, our paper, but nevertheless. It turns out that formal structure is very similar, particularly the Manea paper, actually the Abru Manea paper. It turns out the result is almost identical, but for very different reasons, because they are modeling something very different. And if I have time, I'll mention this paper in somewhat greater detail later on.
What does reciprocity mean?
Can I hold off on that? I mean, you'll see what we mean. Basically, if you don't give the favor, I ask you for a favor, you don't give it to me, then I'll break the relationship. And then you cannot get a favor from me in future. So that's the idea.
That's like punishment, but
Yes, it's a bilateral punishment. So here's the formal structure of the model. Please stop me whenever you have questions. Don't get fooled by what he said. I won't bite off your head. So agents belong to an initial social network, which we will denote by G. When I say social network, I mean a particular G would be, let's say Jivant and I have an interaction with each other. So then I'll say that we are neighbors in the network. So I and he's I, I'm J. Ij belongs to the network. So that's what we mean by a network. So a network G is a set, a collection of such pairs of agents or pairs of nodes in a graph theoretic sense. So the network, initial network is given, but it's going to evolve over time in the sense that some links will get broken because some I will go to some J, ask for a favor, J will say no, and then that link will get broken. So the network gets finer and finer over time. And time is discrete and runs, the time periods are 0, 1, 2, etc., 1, 2, etc. At each time t, one agent is picked at random with probability 1 by n. That doesn't matter, it could be any probability. Probability is adding up to 1. This agent will need a favor, and so favor means she has to go looking around for some neighbor in the network to whom she can ask for a favor. Okay. And a partnership is going to be a reciprocal arrangement or agreement to exchange favors.
so you're starting with a completely connected network?
No, it's not a complete, connected, but not complete.
So you're saying it just gets finer over time?
It gets finer over time because links will break. New links don't form. The population is fixed. You start with, so there's a village community, you start with, there's no out migration or in migration. Providing a favor entails a cost C, which again for simplicity we keep identical across all links. And the flow pay of V is also identical, yes? I can't hear you.
Node is selected randomly with 1 by n probability. So this node is selected by a node within the graph, or is it a new node?
No, it's exogenous. Everyone, so think of you needing a favor so we are all in this room and suddenly some idiosyncratic shock occurs. I mean, I shouldn't say idiosyncratic shock actually. Someone is picked you toss a coin and someone is picked at random. So V and C are identical, so it's in that sense it's a very simple model. So agents are perfect substitutes, both in giving favors as well as in terms of, incurring costs as well as receiving benefits. All agents also have the same discount rate, delta. So if a partnership forms and if it's going to be sustained over time, then capital V is the value of the partnership, okay? Because in any period 1 by n, you either get a favor or you have to give the favor. So V minus C is the probability, is the net benefit, the per unit net benefit, the per period net benefit. That happens with probability 1 by n, and then 1 minus delta is the discounting. Okay. So if so the process runs as follows. So if some agent needs a favor and is not yet in a partnership, if you are in a partnership, then there's nothing to be said. You have sort of moved away from the network and you keep on exchanging favors or giving favors. So there's nothing much else happening. But think of those who are not yet in a partnership. If agent I needs a favor, then he will ask all his current neighbors in the network one by one. It helps the proof. Actually, if we say that the sequence in which neighbors are asked is also random, that's not absolutely important, but that's the formulation I'll stick to. And then each neighbor, when he or she is asked, says yes or no. Yes means okay, I'll give you the favor. No means I won't give you the favor. And then what happens? Well, pretty obvious. If neighbor J accepts, then J pays the cost C and the partnership is formed. So it's important to realize that if J is asked for the favor, then the immediate action is, well, he loses C, and then he gets the capital V from tomorrow onwards. So his benefit is minus C plus delta V, capital V, delta capital V. Okay. Whereas if I get the favor, then my benefit is V plus delta capital V. On the other hand, if J rejects, then the link Ij is deleted, and then I goes to the next person in the sequence, asks for the favor, and then so on. So if everyone that I goes to rejects I, then I gets isolated and he gets 0. You can delete him from the network. He's inconsequential in future.
We're talking about agent I needing a favor and then trying to look at sequence of neighbors and asking them a random. Are we considering the transaction cost of I in this?
There is no transaction cost. Everything's happening very, very fast. It's all happening within one period. So there's no transaction cost.
Even when it is in sequence?
Yes. If there is a cost, it doesn't really matter. You can take it out from, if the cost is small, you just subtract it from small v. So
J is paying C.
J is because the cost of, if you're asked for a loan, then you have to give the loan right away. So you incur, if I go to you and ask for a loan, then you have to give me the loan. So that's a cost to you. If I ask you for 100 rupees, then you have to give 100 rupees. That's the cost to you. But if you say no and then I go to Preetha, then of course there's an epsilon time in my going from you to her, but I don't incur any cost in doing that. That's the assumption.
So what do you mean when J accepts, they leave the network?
If J accepts, that means in future J and I will always exchange favors. So at least in equilibrium, that's always going to be the case.
So when you say the network dynamically evolves, I thought that a link which is optimal now can be broken later based on the current scenario of the network. So that's
What I mean is that either a link breaks.
So why the link break?
If J says no, then the link IJ breaks. Then I doesn't trust J anymore, so I is not going to give J a favor. That's the assumption we are making. That's
So acceptance does not create the formation of a link. Link is just something exogenously already given.
yes. That's the link is from the social network G, which is exogenously given. It's who you know. So we are going to look at Markovian strategy. So here in this context, what was meant by Markovian strategy is that for every agent it determines a response decision, yes or no, and that's a function of the current network and the identity of the person who's asked for the favor. In other words, what has happened in the past is irrelevant. Okay, that's a standard definition of Markov. And so a Markovian equilibrium is going to be a collection of Markovian strategies such that each agent chooses his optimal response after each history. The equilibrium is strongly efficient if it maximizes the sum of utilities of all the agents, and on the other hand we are going to use a slightly weaker notion of efficiency. Here it just means, in our case, efficiency means that for any realization of needs, remember I have said that agents are picked at random to need a favor. For any realization of these needs, for any chance move that can occur, all the Markovian equilibrium of the game are efficient in the sense of maximizing the number of pairs that form. Okay. So let me give you an example of so far.
The assumption that every period the person who needs the favor is drawn randomly. What if we were to weaken that and the fact that I needed a favor this period influences the probability that I need a favor the next period. So would we be able to use Markov strategy? Then history dependence would weaken.
Yes, because then the future will also depend. Yeah, but then lots of it becomes very complicated. As soon as you move away from Markovian strategies, it gets complicated. So we haven't looked at that.
In case if I ask for a favor and J accepts a favor, you told that that link is separated from the network.
Because then they have formed us.
But it is not reciprocative that way, because it's not the other way around that if J asks a favor and I accept it. So because now J can't participate in the network anymore.
But J doesn't have to, right? Because if I and J have formed a partnership, then they.
Partnership, because it was a one-way partnership in a way, because I asked for a favor with J returned, but not the other way around.
But in future, if the other person needs a favor, his favor will be reciprocated.
So it will be surely reciprocated.
Because in equilibrium it will be, because now if they leave the part, so the idea is that if J knows that I is not going to return the favor, then why should J incur a cost? So to make things more concrete, let me go through an example. Okay? Can I use a board somewhere? So think of a simple line network, just 4 players, 4 nodes. Now here efficiency means that 2 pairs should form, because that's, you can have a pair 1, 2 and 3, 4 forming. Okay. Now the question is, given our model, is that going to happen no matter what the sequence of needs? Okay. So for instance, if 2 needs if 2 is the first person to be called upon to play, to require a favor. If 2 goes to 3 and 3 says, okay, I'll give you the favor, and 2 and 3 form the partnership, that's bad news. It's bad news because then 1 and 4 will be isolated. Then only one pair can form. So we need to rule that out. Now, in our model, why is that ruled out? Well, because if 2 goes to 3 and asks for a favor, 3 is going to refuse. 3 is going to refuse because 3 knows that 4 has no one else to go to. Okay. So 3 is sure, 3 has insurance in the form of 4. So 2 goes to 3, 3 will say no, that link will get broken, and then you have these 2 isolated pairs 1 and 2, and they will surely form a 2 partnerships.
But why would we care about that? Because
Huh?
why would we care about whether it is formally equal to 2 or 4? Because it's indifferent between.
No, because if 2 goes to 3 and asks for a favor, and 3 says yes, then 3 incurs the cost of C this period. So 3's payoff is what? It's minus C plus delta capital V. If 3 says no, then its payoff is delta V.
No, that depends because
No,
will be selected the next period or not.
that's taken care of in the formula V. It's everything. It's V. It's V is small v minus C divided by n 1 minus delta. So next period with probability 1 by n, 3 will require a favor, he can go to 4. With probability 1 by n, 4 will require a favor, he can go to 3. So that's why you get the v minus C term, that everything is divided by n. So the randomization that's taken into account. So the important thing is that giving a favor involves, if C is positive, it involves an immediate cost. So if the future benefit is the same, whether I say yes or no, then why the hell should I say yes?
If you open it up to bargaining, 3 would be in a nice position, right? To bargain 2 and at 4, because 4 has nobody else to access. So do we look at bargaining in these? So here B and small v.
Okay, since you're talking about bargaining, let me mention that I told you the Abru-Manea paper. That has, so in their model, the agents are, what was it? I think buyer and seller, something like that. So there's a group of buyers, there's a group of sellers, they're connected, and then any pair, again I think it was selected at random, and then the pair have to bargain over the price. Now there is an infinite number of equilibria in their model. The Markovian equilibrium is inefficient, and they construct a very elaborate system of punishments to show that, and again in their model, if a buyer and seller agree on the price, they go away. So if 2 and 3 agree on the price, they will go away, and then that's bad news. They construct an elaborate system of punishments so that some non-Markovian equilibrium is efficient. We don't have any bargaining, but we have a Markovian equilibrium which is efficient. And in their model, the Markovian equilibrium is inefficient.
So if 4 goes to 3 for the favor, then he can reject that because he thinks that the next time it might start and he gives a favor he can get from.
Sorry?
If 4 was for favor to 3, then 3 can reject that, right?
If 3 rejects that, then 3 will be then that pair, then that link will be broken. And then 1, 2, 3. See, if delta is high, now look at the network 1, 2, 3. In the network 1, 2, 3, if 3 is the first person to require a favor, which will happen with probability 1 by 3, 3 will go to 2 and 2 will say no, because 2 has a captive agent 1. So with probability 1 by 3, 3 loses out. So if I say yes, I am 3, I lose C, but I get delta V. Delta V is, but if delta is large enough, delta V goes to infinity. Remember the formula, it's delta is minus delta is in the denominator. So I pay a finite cost, but I get a potentially infinite something approaching infinite benefit. So I will always say yes.
So you said 3 selected, 4 drops out, and 3 selected probably 1 by 4.
In the next period.
So
Sorry, with probability 1 by 4.
okay, so
Yeah, with probability 1 by 4. No, with probability 1 by 4. But thing is, with probability 1 by 4, I can get 0. No, the thing is that 4 is not dead. 4 remains. 4 needs a favor, he has no one to go to. So, it also so it's clear that here in this model, in this line, you'll always get efficiency. Of course, that's almost obvious. As soon as I tell you this, it's clear. What we want to show is that this is a general phenomenon. It does not matter what the network is. No matter what the network, the underlying logic remains the same. Okay? But then for that we need to build some machinery, which is what I'm going to do now. This is not really important. It just simply says what's a matching? Well, a matching is a collection of edges ij such that no pair of edges has any vertex in common. Okay. In other words, J can be matched only to one agent. That's a feasible matching. And maximum matching means that given the graph G, you can't form more than the maximum number of matches. We are going to denote mu G to be the matching number of G, which means it's the size of the maximum matching. So in this here, mu G would be 2. If you have a cycle of size 5, again mu G is 2. Some terminology, what we mean by essential is that a node is essential in G if G belongs to all possible maximum matchings. So for instance, if you think of a star is there's one central agent, the hub, and the hub is connected to different peripheral nodes. So there, of course, and the peripheral nodes are not connected to each other. Then the mu of the star is 1, only one pair can form, and the hub must be in every such matching. So the hub must be an essential node. If you have n agents, an even number of agents, and you have a complete graph, then every node is essential. If you have a complete graph with n even, then n by 2 is the matching number of the graph, and every agent is in some in every possible matching. Everyone's connected to everyone. So because essentiality is crucial to our proof, now for some reason you can't see this, what's happened? I don't know what's gone wrong. I think this was, these lines are missing. So this graph is this is connected to this, and these are connected here. So there is a square and then a sort of a hat on top, a triangle on top. Okay. So for some reason these lines are missing, I don't know why. I could see it on my screen. Now here in this graph, nothing is essential, no node is essential. This node, so here there are 5 nodes, this is a square, etc. So the matching number is 2. You can check that, delete any node, and then the matching number of the remaining graph is also 2, which means that no node is essential. On the line of 5, the red nodes are essential. On the line of 5, the matching number is 2, and if you delete any of the red nodes, the matching number drops to 1. This again, for some reason, this should, let's forget this. So this is a, well, bad pun, but this is an essential lemma. It's an essential lemma, and because we are going to use this repeatedly, well, we are going to use this intensively. It has many parts. Let me go through them and I'll explain some of the parts. So this says if I is essential in G, then the matching number of G must be 1 more than the matching number of G minus I, where G minus I is the graph obtained from G by deleting node I and all of I's edges. This is clear because suppose it is not, suppose mu G is equal to mu G minus I, that means that there is some maximum matching in G minus I mean no maximum matching in G minus I obviously includes I. But then if it's equal, then every maximum matching in G minus I also remains a maximum matching in G, but then I is not in that matching. So then I would not be essential, contrary to what's asserted here. If I is essential in G, then there must be some ij in G, some neighbor j of I, such that j is not essential in G minus I. What is the proof? Well, if I is essential in G, then this is true. If every j is essential in G minus I, then mu of G minus ij must be equal to mu of G minus I minus 1. So putting these two together, that would mean that mu G is equal to mu G minus ij plus 2. But you have removed only one ij, that's one pair, so the matching number can't fall by 2. So that's the idea. Similarly, you get these relationships. I won't go into the proof. Okay. So the main theorem in this part says that for high enough delta, every social network supports efficient equilibria in the sense of sustaining the matching number, the formation of the maximum number of matchings in that sense, in the sense of this story graph. To see sort of grasp an idea of the proof, let's think of what are the equilibrium strategies in any again when I say equilibrium, I mean Markovian equilibrium. So basically the equilibrium strategies will have the following components. If J is essential in G minus Ij, then J is going to reject I's offer. Well, the idea is that, again, let's think of this. I'm sorry. Think of 2 and 3. Think of J as being 3 and 2 as going to I and asking for a favor. So if this link is broken, then you get 1, 2 and 3, 4. and 3 remains essential in the graph, in the resulting graph. Then 3 has no incentive to ask for, to accept i's request. The idea is that essential nodes are going to be able to form partnerships. So, if an innocent, sorry, this is where I was. If j remains essential in G minus ij, then j is not going to accept i's request for a favor, because again the idea is that if he accepts, then he incurs an immediate cost, but his future benefit remains the same. So he is better off refusing and going into the smaller graph. On the other hand, if j is not essential in G minus ij, then j accepts i's request, because it's possible that tomorrow I may not become essential, and then j should accept. If you think of the 5-person line, that's what's going to happen. And so these are the only equilibrium strategies. And so using the essentiality lemma, we use backwards induction to show something like this, that if I is essential in G, there will always be some neighbor j who will accept i's request, and then that link forms. And if j is not essential in G, then j gets rejected by everyone. Okay. So that gets you into finer and finer networks, and then you can use, so you can start with the network of just 2 people, their life is very simple, the network will obviously form, and then you can build your way, sort of assuming that any network, that the result is true for any network of size k, you add another agent, follow these equilibrium strategies, and then depending on what the network is like, whether the added agent is essential or not, you get the result. So following these, basically following these that equilibrium strategy, how will the network evolve? So first, if an inessential agent is chosen, then I is the inessential agent, then you move to the network G minus I, because all of I's neighbors refuse the favor, refuse the request for a favor. And then in G minus I, all essential agents remain essential. All agents who are essential in G remain essential in G minus I. It's possible that some inessential agent now becomes essential. Okay. That depends on the structure of the network, but that can happen. For instance, if you start with the 5-person line, then the extremal agents are not essential. But if you go to the 4-person line, so start from the line of 1, 2, 3, 4, 5, 1 and 5 are not essential. Then if 1 asks for a favor, 2 says no, and now you get a 4-person line, and then 5 becomes essential. So that's what this is referring to. So if an essential, on the other hand, if you start with an essential agent I, then he forms a network with some agent j, ij leave, and then you're left with the graph G minus ij. Okay. So that's how, basically how it evolves. I'm going to skip this. Now, this is all for high delta. Remember, the theorem is for high delta. Suppose we go to the other extreme and look at what's going to happen for low delta. The result will obviously not go through, but can we say something about the parameters? Can we make any comparisons at all? Now, it's very difficult. This comparison is difficult in general. What we can do is we can compare, we can ask ourselves, for low delta, is the line, is it easier to sustain equilibrium in the efficiency in the line versus the complete network? if you just look at if the two candidates are the line versus the complete network and let delta is low, which would sustain, which is more likely to sustain the efficient equilibrium? Why? Huh? No, in the if you take the complete network, if n is even, then everyone is essential. So the answer is indeed it is the line is easier in, I mean, efficiency is easier to sustain in the line than in the complete network. I mean, in some sense I would have thought, I mean, in some sense it is less, the intuition should go the other way, because if you have more links, you would think that, well, there are more possibilities of pairs of agents forming, so maybe the complete network is better. But it turns out no, and for the following reason. Let's take the case of an even number of agents, because that's easier to work with. So in a line of size k, let Vk be the value of the extremal agent in the line. So if you have a line 1 to 4, then V4 is what 1 can expect in the line, or what 4 can expect in the line. Now, one can show that Vk is increasing in k. So the longer the line, the higher is the value of the extremal agent. That's what this means. Now consider any agent in the line, and someone, his neighbor goes to him and asks for a favor. When should he accept? And that's given by this equation. If he accepts, then he gets delta V, but he has to pay the immediate cost C. So it's delta V minus C. If he rejects, then he becomes an extremal agent. You're in the line, so if you reject, then you become an extremal agent, because the IJ link breaks. Okay, and suppose k is the size of the line when link IJ is deleted. Now this condition is hardest to satisfy, given that Vk is increasing in k. It's hardest to satisfy for n minus 1. Okay, so it's hardest to satisfy for agent 2, because if 1 goes to 2 and if 2 rejects, then he can look forward to Vn minus 1. So it's more likely that 2 will reject rather than any other agent in the line. Okay. So let's keep this in mind, that 2 will accept in the line only if delta V minus C is greater than or equal to Vn minus 1. This is on the line. On the line, Vk is increasing in k, because it's more likely that in future he will be able to form a partnership. One and 4.
We had 6. 6, the B of 6 is more than B of 4.
That's what this is saying. But only for the extremal agents.
Only for the, yeah.
Or what it's saying is that B of 4, so player 1 can look for, on this graph, gets less or the expected value for player 1 is less here than it is on if there are, if there is an added number 5 or 2 more 6 and so on.
So you're saying that the constraint is strongest for
2,
agents next to
the extremal agent, because if they refuse then they become
they have the longest
the n minus 1. On the other hand, if you consider a complete network, then you can actually again you can compute the value, it's wk, that's given by this formula, and this is clearly increasing in k. Okay. So delta, and you can show that Wn minus 1 is greater than Vn minus 1. So because think of this as the opportunity cost. So if a complete graph is sustainable, then the line is certainly sustainable, but not necessarily the other way around. Again, this is all for small delta. So the essentiality lemma, that doesn't go through. Now I'm almost out of time. Well, I'm getting there. This is for low delta, and what we mean by low delta, we don't quantify. It's going to depend on all the parameters, V, delta, V, C, yes. Yeah. So the other part is, what if we now move to the case of C being negative, in other words, marriage or couples, formation of couples, presumably that's typically that's beneficial for both. Okay. I won't go through the results in detail. Let me just again illustrate here. So what's going to happen on the line? Clearly you cannot get efficiency. Why? Well, because if 2 goes to 3, if C is positive, sorry, if C is negative, then you will always form the link. So if 2 goes to 3, 3 will say yes, and then 1 and 4 will be isolated. So when can you get efficiency? Sorry? No. No, efficiency in our case always means no matter what the sequence of needs.
Right.
So you can't say.
Right.
So a graph is bipartite if the following is true. You can partition the set of nodes into 2 sets, sets A and sets A and B, such that agents in A are not connected and agents in B are not connected. So for instance, you can think of buyers and sellers, or men and women. Okay. So men are not connected to each other. So it's going to be bipartite if men are not connected to each other and women are not connected to each other. And it's going to be a complete bipartite if every man is connected to every woman and every woman is connected to every man, but the men are not connected to each other and the women are not connected to each other. Okay. So again, let me instead of going through the slides, it's easier to explain the result on a graph on the board, and that's what I'll do. Okay, so suppose this is the set B, this is the set A. Now this is not a good. Now here if this is the graph, then the matching number of this graph is 3, because 3 pairs can form. Now notice that this is not complete bipartite. So if this is the graph, then it is a complete bipartite graph, because every player in A is connected to all the players in B and vice versa. Okay. Now clearly here you must get efficiency. Why? Well, you must get efficiency because if let's say any agent in A requires a favor, if he goes to anyone, he can only go to players in B because he is not connected to anyone in A. If he goes to anyone in B, if that disappears, suppose he goes to this player, they form a partnership, then the remaining subset has the same structure. It remains a complete bipartite graph. So that's the important feature of a complete bipartite graph, namely you take out any ij, then G minus ij remains a complete bipartite graph. So clearly that's sufficient for attaining an efficient number of pairs. What's interesting is the necessity part. You actually need this to be a necessary condition if there is a first, if it's a complete, if there are an equal number of agents on each side. If there aren't an equal number of agents, then in any case the matching number is smaller. Okay. And you can construct examples to show that if it's not a complete bipartite, then if you remove one pair, any specific pair of agents, then the remaining set will have a structure such that you can't form the matching number. Okay. Basically, that's what we show in this paper. And the important thing is that when C is negative, that is there's a benefit, then pairs will form immediately. There's no incentive for any agent to refuse a favor. So you must make sure that the wrong pairs don't form, which is tantamount to saying that essentially nothing is to be able to sustain efficiency, the network must be such that no pair is within quotes the wrong pair. So very briefly now let me turn to the experimental part. Now of course any experiment must end in finite time, whereas in the theoretical model we have, it's an infinite game. Okay. So we have to do so the experiment, in other words, the experiment can't be a complete, cannot completely capture the theoretical model. So we try to go as close as we can. So what we do is the following. First, only participants who are not yet in a relationship are chosen with equal probability to ask for a favor, and they can only ask their agents in the network. And the process ends when no new partnership is formed. This must end in finite time, because any time someone needs a favor and gets the favor accepted, that pair forms and they leave the network. So you get, and there is no repetition because of the first part. Okay. Moreover, the values obtained, the benefit is V if a favor is given, and the cost is C. That's also fixed for, it's uniform across all links. That's also in the theory model. So either an agent gets V minus C if the agent grants a favor, or he gets V if he requests a favor, and we fix these values, V equal to 20 and C equal to 8. We want to show well that the equilibrium behavior in this finite, actually the equilibrium behavior in this finite game is going to coincide with the equilibrium in our infinite game. The networks that we consider in the network in the experiment are the following. So the 4-person line, the 5-person line, then this triangle with one node hanging out but connected to one of the agents, then a square, and then again this agent, and this is the most complicated. Now, in terms of analysis, or in terms of the number of steps ahead that an agent has to compute, the network is the complexity of the network increases as you go down the line. Sometimes this is the easiest network to handle, this is next, and so on. So subjects go through these networks in sequence, starting from the 4-person line, and each is repeated 5 times. Each network is repeated 5 times. So any one subject plays 25 times, and they are randomly rematched at the beginning of each period. Within each group, one active agent is randomly chosen to request a favor. He has to decide, the J who receives the request has to decide whether to accept or not. Acceptance means the partnership is formed, they leave. Rejection, and then both leave. Rejection means that that particular link is broken. And of course, if all neighbors refuse, then the original player gets 0 and is cut off from the network. The remaining agents are informed of the current network. Now, it turns out that about 80% of the responses conform to predictions of the theoretical model. This sounds like saying wow, but there are qualifications. What are the qualifications? Well, the distribution of best responses, or not best, the distribution of correct responses is not uniform across the networks. Okay? In particular, the presence of cycles, for instance, all these networks 2 to 3 has some cycle or the other. This is a simple cycle, but then these become longer, and this is the most complicated of all. Subjects seem to perform well in lines, but less so in circles. Extreme positions are more likely to do the right thing. They're more likely to do the right thing partly because the right thing is to accept if you are in an extreme position. If you reject, then you get 0 for sure. Now, central players are more likely to accept when they should reject. So, the mistakes from the theoretical prediction typically go in one direction, namely you accept when you should reject. But for the extreme players, the right decision is to accept. So it's not surprising that they don't make a mistake. We do a probit, well, when I say we, I mean Stefan and Minzu, do a probit regression where the dependent variable is the proportion of best responses, and the independent variables include the following. B reject, this is a dummy variable, it takes value 1 if the best response is rejection, value 0 if the best response is acceptance. this, the absolute difference between expected value of rejection, this is the difference between the expected value from rejection and acceptance. Captive, again, this is a dummy variable. This takes value 1 if player 1 has a captive neighbor. So in the line of 4, 2 and 3 have captive neighbors. So 2 and 3 would take value 1 in this variable. 1 and 4 would take value 0. And there's a measure of risk aversion. I'm sure you can't see this. Let me try to. Is there a way of? No, I'm sure. So basically, the B reject, that has significant and it has a negative sign. Okay, so when the best response is to okay, if the best response is reject, yeah, that should have a negative sign. It has. The absolute difference, that has a positive sign. Captive, that has again a positive sign. If you have a captive agent, then you're more likely to take the right decision. Cycle, it's not significant, but then when you interact it with the cycle, again it doesn't change. Risk has a negative sign. So the riskier you are, the less likely you're more likely to accept when you should reject. Why? Well, because if you accept, you at least get V minus C. If you reject, you're scared that other players later on would do the wrong thing, and then you might end up getting 0. So again, there are differences from the theoretical prediction, but to some extent we can explain why.
How are you toxic for risk in the regression? What is the toxic for risk?
So there's a measure. So they were given a test, separate test. Yeah. Again, I forget the exact test, but that's described in the paper. But that's a separate test of risk aversion. Yeah, I don't remember, but yeah, I should know. But it's a separate test. So the absolute difference between acceptance and rejection, this increases the probability of making the correct decision. So if acceptance is, so the larger the difference, the absolute value, because it's always going to be negative if you don't make the right decision, then the larger the difference, you're more likely to take the correct decision. Importantly, there's also some learning effect. In the sense that, remember, the subjects play 5 times, the decisions towards the end are closer to the theoretical prediction than the decisions at the beginning. So players learn how to play the game, and they are more likely to, as I said, if you have captive agents, then you know that, well, you are assured of a partnership, so you're more likely to take the right decision. And again, risk aversion, that again, as I said, explained earlier, that makes sense. The more risk averse you are, the more you are willing to accept, even though the right decision is to reject, so that you make the wrong choice. Because the wrong choice is always typically in one direction. You accept when you should reject, according to the theory. Okay. So basically, so just to conclude, So what do we have in this model? Well, as I said, we have, this is a somewhat stark model of formation of bilateral partnerships, where we focus entirely on reciprocity as a driving force sustaining relationships, these partnerships. And within this, what we try to do is look at the structure of the networks, what kind of network structure will sustain efficiency. Well, again, by efficiency we mean formation of the largest number of possible bilateral partnerships. It turns out that when the cost of forming links is positive, so players think twice, they don't immediately jump into partnerships. That's good for sustaining efficiency, because any network, irrespective of the structure, will sustain efficiency. On the other hand, if the cost is negative, so there's a benefit of forming a relationship, immediate benefit even of giving a favor, then clearly players will jump into relationships, and that's bad for efficiency, for formation of the efficient number, because wrong pairs can form. Okay? As I said, there's also an experimental part that to some extent supports the theoretical predictions. Okay, I'm willing to take questions. We have some couple of minutes, I think.
So the efficiency of the whole graph is maximized when individuals are also maximizing relativity.
That is going to depend on the value of delta.
So in these, the experiment, the case that you tested, how close were you to efficiency?
We are looking at just the formation of the maximum number. Sorry?
The complete network would lead to the efficiency in either case.
Yes.
Right? Complete network would always lead to efficiency.
Because the complete network has the property that if any pair leaves the network, then the remaining remains complete. So sorry, repeat that.
Sorry, I was just trying to connect it. So I was just trying to connect it to managed markets and why managed markets might remain not optimally connected. And so basically in the underlying you have like a big social network. And then you're searching on the social network for your partnerships. And so partnerships will be inefficiently formed if, for instance, so the bridge players form a link and
right.
if
So
you're not able to search, then the remaining people are
they get isolated. That's right.
and they're not able to search.
Whereas in the complete network, that can't
That
happen.
will never happen, right? So you don't have.
We're assuming common knowledge about the network.
Yes. Not just common knowledge about the network structure, common knowledge at each stage. So when, but that I don't see. I don't think the interesting. Sorry, at each stage that part is not important, because if you know the initial network, then you should be able to predict what has happened.
But that doesn't happen in your experiment, for instance, right? Like people are, whatever this thing that's being captured by this potentially be captured theoretically by saying that what if I don't think my future partners will act rationally. For instance, if there's limited rationality, then I would accept.
But that's why risk aversion seems to play a role in the probit regression. I mean, risk aversion should not play any role if everyone behaves rationally. But I might accept, if I'm highly risk averse, I might accept when I should reject, because I think that players later on may do the wrong thing.
Right. So if I'm worried about the rationality, so that's my risk.
Right. I'm worried about other people's rationality.
Exactly. So that would be true in your theoretical model also. in that sense.
In our theoretical model, everyone is
Now,
rational.
if you broke up the rationality in the theoretical model, then
I don't know how to model irrational.
yeah, I know.
How do you model irrationality?
But in essence, in this
You know, epsilon behaviors, like, does that work? Like, by some, like, even if they should rationally accept, they take some probability they take the wrong decision.
I don't know what will happen. Sorry?
So in this framework, there is no network externality per se. So what is happening between one pair is not really affected by what is happening elsewhere in the network. I mean, essentially, it is
No, but what can happen elsewhere in the network can affect your decision. That's exactly what is happening in the experiment.
no, theoretically, because it's always consistent with
No, in the experiment, I'm saying in the experiment, risk aversion plays a role because what happens in the remaining in the other part of the network does affect you. So if someone is irrational and makes the wrong choice, that affects your payoff.
I'm not, I mean, that part I understand.
Hmm.
But what I'm trying to get at is that all of these variables and the probabilities are all sort of unconditional. If you make them even remotely conditional,
What do you mean? I
conditional on the, so suppose the payoff that, so every period I have a requirement of a favor with one of the improbability or something like that. So what if in my lifetime I will need 3 such favors? So the fact
then
that
you're a lucky man, but
sorry.
I'm saying then you're a lucky man.
No, I mean, so basically the point is that in that case, what happened, I guess I'm going back to the point that you raised at the very beginning, that if there is a little bit of history dependence in some way, either through the strategies or through the payoffs or through the number of,
Or through the favor draw,
through the favor
drawn to the
then how robust would be this kind of cases?
it's a completely different setup.
I think we talked about the following. Suppose there is so numbers P1 to Pn with probability P1, player 1 requires a favor and so on, and they add up to 1. It doesn't have to be P1, Pi doesn't have to be equal to 1 by n. Yeah, but you're saying something else. You're talking about history dependence. So at the end, after you've already used up required 3 favors, then you sort of cease to exist, because you're not going to give any favors in future, because this is reciprocity. If you have already received 3 favors, then you're not going to give any favors in future, but then you're less likely to receive the 3rd favor. Who will give you the 3rd favor? You will never get the 3rd favor. Because I know that once you have received the 3rd favor, if you come to me, you have received 2 and you come to me for the 3rd favor, I'm going to say no, because I know that you're never going to reciprocate my needs. And that's true about everyone. because if you have received only one favor, then you are still likely to give favors, but then you are more of an active player when you have not received any favor, slightly less when you received one favor, and not at all when you received two. But that's a highly non-Markovian model, and I don't think that's tractable for analysis.
If there are no other questions, then thank you very much.
Thank you.